Okay, so this is the final hour of Physics 1C for September 8th. All right, so we are going to talk about how we calculate speed by using this idea of electric potential. So we have a proton that's released from rest at point A, and that's up here, in a uniform electric field that has a magnitude of 8 times 10 to the 4 volts per meter. The proton undergoes a displacement of magnitude d equal to 0.5 meters to point B in the direction of the electric field. Find the speed of the proton after completing the displacement. And it says that it's released from rest, right? All right. Oh, and it says right there, VA is 0, and we want to find VB. Okay. Any questions about the setup of this problem? So let's write down the relationships that I've told you so far. One of the ones we wrote down was that the change in potential energy is connected to change in voltage as long as I divide the potential energy by Q. This is one of the relationships that we had. And then the other relationship that we had was that delta V, that does not look right, delta V was equal to, if it's a uniform field, negative E dot change in S, where change in S is basically displacement. Particle moves from A to B, so we can solve for this if we want to. We can figure out what delta V is. Notice in the problem they've given us electric fields, 8 times 10 to the 4 volts per meter. So that's not voltage, right? And I think what our goal here is to just connect the change in voltage to the change in potential energy, and to use that to find the change in kinetic energy and relate that to the velocity at this point. That's kind of our goal here. All right, let's solve for this part first. Displacement goes from the starting point down to here. Oh, it looks so bad. So our displacement goes this way. That's our delta S vector. E and delta S are parallel to each other. And delta S has the magnitude of D. So delta V, once again, just becomes E times D with a negative sign. We know what the value of E is right here. We know what the value of D is as well. So we can calculate what the number is for this here. If I want to, yeah, we might as well. So change in potential is going to be the electric field, which is 8 times 10 to the 4 meters, or volts per meter, multiplied by the distance d, which is 0.5 meters, and you have to remember there's a negative sign here. So delta V then should be equal to 4 times 10 to the 4 volts. And there's a negative sign on top of it. Does that make sense to you guys? Any questions? Now, this relationship that I've written right here, a more common form that you're going to see show up when you're doing your homework, and if you look at the equations in any physics textbook, is that you just connect the change in potential energy to Q multiplied by delta V. This is a really handy relationship. So it's worthwhile to commit its memory for this homework for sure. Now, why do I want to use this? Well, we know that there's a way that you can connect kinetic energy and potential energy. And it's by using this work-energy relationship, that the work done by non-conservative forces is always equal to the change in mechanical energy of a system, which happens to be equal to the change in kinetic energy plus the change in potential energy. I kind of told you, and in a really kind of hand-wavy way, we basically proved that the electric field is a conservative field. We didn't really prove it, but we showed in go back up here. In this case here, that the path to go from A to B and from A to C to B, they have the same change in potential, which implies that it's a conservative field. It doesn't really matter what path you travel along. So that means that, what does that mean for the work done by non-conservative forces in this problem? Are there any non-conservative forces that are acting? No. Alright, so let's fill out the rest of our equation then. Changing kinetic energy is 1/2 mass times final velocity, which is called VB in this case, squared, minus the initial velocity, which is called VA in this case, and then plus Q times delta V. We just literally straight up replace change in potential energy in this problem to just Q times delta V. We're also given the fact that VA is 0, so we can make that 0 right there. And we can solve for VB, and I believe what we're going to get is, I'll do it in 2 steps. So let's move Q delta V to the left-hand side where it's going to become negative. And then the next thing we want to do is to just solve for VB. So we'll have 2 with a negative sign, Q delta V divided by mass, square root. All of that is equal to VB. And then we just need to plug the numbers in. That's pretty much it. It's pretty straightforward. You guys have any questions? A lot of your problems are just going to say things like proton, alpha particle, electron. You're going to need to go look up in a table that the mass of the proton is going to be equal to this number and you're also going to need to write down that the charge of the proton. So you need those. But then we plug them in here, we'll get an answer. If you guys want to go ahead and plug those into a calculator, go ahead. So it's -2 times the charge times delta V. Delta V is negative. And then divided by the mass, which is right there. What do you guys get if you put that into your calculator? About 2 times 10 to the 6th? Sounds about right to me. It's not the only way to do this. We could have calculated the force. We could have done force equal to mass times acceleration. And we could have figured out what the speed is here by doing that as well, by using kinematics equations. That would have been one option. But energy is always a good option, and energy is going to work in even more cases because it's also going to work in situations where the electric field isn't constant over the region, which will be what we look at next. All right, there's a pretty simple problem. You're going to have problems like this on your homework. Any questions? Just remember this connection here. And remember that you can use energy to solve these problems. Okay. So do other people agree that you get 2 times 10 to the 6th meters per second? Before I move on? It's pretty easy to look at this, actually, because it's 1.6 divided by, those basically cancel out. And then you've got 2 times 4, which is 8. But then you've got 10 to the 4 makes this 10 to the negative 15. 15 divided by 27 would be negative 15. You're left with like 12. So this is 8 times 10 to the 12. How does it come out as 2? Alright, now I have to actually plug this in my calculator. Did you delete your answer time? It's okay if you did. I think you must have left out the 2. So the answer is... Okay, I know what the answer is now, then. It's going to be 2.8. That's going to be the answer, right? No? Okay, I'm just plugging this in. It's going to be like 2.8. Okay. Yeah, there we go. See? Sometimes you just do things in your head. Or at least, like, check to make sure that the answer you get makes sense. So, it's 2.8. Seconds? Oh, how did we get seconds out of this? The meters per second? Oh, okay. Well, let's look at the units. That's a great question. So coulombs, okay, times volts. I told you volts were joules per coulomb. And then we're dividing by kilograms. And we're square rooting everything. So this goes to... The coulombs obviously cancel, and you need to replace the joules. Maybe you can already see it now. But a joule, if you remember, is a kilogram multiplied by a meter squared divided by a second squared. And if you didn't remember that, you know, it's kilograms times meter squared per second squared right there. And you divide by kilogram. Meter per second. There you go. Great question. Thanks for asking that, because I know these units are new to you guys, so it's definitely important to be thinking about how to check your work. You always want to be able to check your work, right? And this is a great way to check your work, is to make sure that the units make sense. Because if they don't, and the volts ended up in the denominator, you might be like, oh, maybe I made a mathematical error somewhere in the algebra. So, and then your question is, this is an alternative to Coulomb's law problems. I don't know how this would be considered a Coulomb's law problem, but I mean, in the sense that the alternative would have been to use F equals ma. That's the alternative. We're using energy here. Definitely energy is going to be easier than F equals ma. You do it in one step as opposed to 2. That answers your question, Ash. Okay, so I keep saying that you can use this definition right here for talking about change in potential. But what if the electric field changes over the region of space where delta S is? Like what if the electric field wasn't constant in this region of space like it is here? Here the electric field's constant. So then, yeah, we have to do integration, exactly. So for an electric field that changes, okay, so if you have a non-constant or a variable electric field, well, now instead of doing delta S is going to become some tiny displacement ds. And then when we say the amount of, work done, that's going to become, instead, before it was basically just like negative, or it was positive actually, right? It was, the work done was basically the force, which is Q times E, and you have to dot product that with now ds. So now if I want to find the total work done, what I'm going to have to do is just integrate f dot ds. That's our definition of how we do work anyway, right? So that becomes integral of QE dot ds. And then we make the connection that the voltage is going to be equal to the negative of the work done divided by the charge. And we end up getting that, it's a change in voltage. This ends up being negative integral E dot ds. And this becomes, looks so bad. I hate writing fast. ds, E. This is our more general definition of what voltage is. That you find the voltage by doing a line integral of E dot ds. Okay? And the simplest example that we can look at of a non-constant electric field would be the electric potential due to a point charge. Because if we can figure that out, we can build on that and talk about the electric potential due to all kinds of different things, just like we did with electric fields. So that's what we want to do next, is we want to talk about the electric potential of a point charge. So let's take a point charge. And let's say that it has a value that we call capital Q. And we think about the electric field lines associated with this object. the electric field lines for a positive charge, they basically point radially out away from it. So like you could have one like right there. You could have one coming out like this. Oh, good. It just did that, huh? Okay. Now I gotta... Okay. We have one going like this. Might have another electric field line coming straight down here. Just all around, you've got these electric field lines coming out of our point charge, right? And they're duplicated on the left-hand side too, but I'm not going to draw those. So these are our electric field lines. That's electric fields. And suppose, just for simplicity's sake, that we want to take a charge, and we want to consider what happens when it moves from, like, let's say, point A right here to some point B right here. Okay, that's the path along which our charge is going to move. And so to figure out what's going to happen, we need a charge. So we place at this location some point charge that we call Q naught, and we say it's going to move from here to here. And we want to calculate basically what the value of delta V is between these 2 points. Okay. Now, in order to do that, we're going to need to define some distances. So let's define... I'm going to have to make this bigger. Which just won't do. Let's define the initial location of our object here to be... Alright. Let's call this RA. And let's call the other distance RB. Do I need to draw that one on here too? Probably should. Kind of drop below it. So then the second distance we're going to need is this point right here. We'll call that R sub B. We're using position vectors now. And we want to evaluate this quantity here, E dot ds, along our line. We already know what the electric field is for a point charge. All around the point charge, the value of the electric field is K times the charge, which I'm using capital Q for, divided by the distance squared. Right? So if I want to evaluate what delta V is between these 2 points, specifically what VB minus VA is going to be, then I need to integrate E dot ds. Well, E is this thing, KQ over R squared. And we can make it into a vector as long as I put R hat right here. So it's KQ divided by R squared. And then I put an R hat right here. We need to do the dot product of that with the change in S. So S is like your path. And our path in this case goes from A to B. And in this case, that is a radial direction, right? So we're just instead going to put dot dr here. We're just going to put dot dr in there. And then we're also going to say that this dr vector, it also happens to point in the same direction as the electric field vector, right? Because of what we chose here. And we could have made it more complicated. We could have moved from point A to some point over here. And we need to do something, but we'd find out that you get the same answer anyway. So that allows us to get rid of the dot product here, so that our integration just becomes the integral of KQ over R squared, just dr. Because the path, maybe I should indicate on here what dr represents. That would probably be helpful, right? Dr represents infinitesimal displacements along this path. Like that's one dr, here's another dr. You could fill up our displacement from A to B by these little drs, right? And they're all parallel to A to the electric field. So that's why we get rid of the dot product. And now we have a pretty simple integral to solve, right? We just need to plug in limits. I said my limits were going to be R sub A and R sub B. No longer vectors, but just the length, RA and RB. And then we can do the integral. What's this integral give us when we do it? Something like -1 over r. Yeah, k and q are constants. So we end up getting negative kq over r with another negative sign. You need the negative sign here because when I take the derivative of r to the -1, you get r to the -2, but you need a -1 in front of it. Yeah. And then we need to evaluate that with our limits, r sub a and r sub b. The negative signs cancel. So this ends up being equal to, remember that we were doing delta v. And we said that that was equal to vb minus va. And now that's equal to negative cancels. So we end up getting kq over rb minus kq over ra. And if we look at this expression right here, I shouldn't box it in, it's not really the final answer. There's a lot of symmetry, right? VB, it looks like VB is KQ over RB, and VA is KQ over RA. So that's really handy, because we can write in general that for our system now, that for a point charge, we can just say that V, at a point in space, you can define the electric potential by just doing K times the charge divided by the distance. That's really simple, right? Voltage is a scalar, electric potential is a scalar, so there's no longer any, vectors, right? And this is an equation where R will always be a positive quantity, but Q can be negative or positive. Okay? You need to put the sign of the Q into this equation. That makes sense? You need to put the sign of the Q into that equation. So we can kind of sketch out what electric potential would look like for this equation right here. Do you guys have any questions before we start to do that? Let's imagine what this might look like for a positive and negative charge and see what's different. So let's say that I take a charge here, and I tell you it's a positive charge Q. And I tell you that that charge Q, let's say, is equal to, what do I want to use? Let's use something simple. Let's use 1 nanocoulomb. Use 1 nanocoulomb, okay? That's our charge, right? And now let's go out to some different distances. So let's say that we go out to a distance around this charge. And let's say that we come out to a point, and I tell you the radius, the distance from here to here, let's say that it's equal to, let's use half a meter. 0.5 meters. Can you guys tell me, what would the value of the potential be along that ring that I've chosen right there? It's an equipotential, right? Because it's one distance r away. What would it be equal to? All on that ring. If the charge is 1 nanocoulomb and the distance is 0.5 meters, what's V equal to? You guys remember what K is? So K is 9 times 10 to the 9. Q is 1 nanocoulomb, so that's 1 times 10 to the negative 9. And we divide by R, which is 0.5. What's the answer? You should be able to do this one in your head if you just look at it. It's 9 times 1 divided by 0.5. That's 18, right? What's left? 10 to the 9 times 10 to the negative 9. Those basically annihilate each other, and you just get 1. I don't know if annihilate's the right word, but whatever. You get 18 volts, right? All right, so right here we have 18 volts. What happens to the potential if we go out to a circle that's twice as big? So now if we go out to a circle and we make it twice as big, what's the potential here going to be? So if I tell you that the next distance here is another 0.5 meters, so that the total distance is 1, it's half, yeah? So this is going to be a 9 volts, and you guys agree it's an equipotential, right? The potential all along that circle is 9 volts. Okay, what happens with another half meter? Does it cut in half again, or something else happen? So now let's do another circle. I'll try to make it the same distance. Oh god. I should have just... No. After I draw it, I have to click something else. Is that look... Yeah, nope. Maybe? That looks kind of okay. So what's this one going to be then? So that was 18 volts and then 9 volts. What's the next one? Is it 6? Yeah, 18 divided by 1.5 now. Is that 6? I don't know. 1.5 multiplied by 2 would be like 3, 27 over 3. What's wrong with me? 12. So this would be 12 volts. Wait. It's not 12. That doesn't make sense, right? I definitely... Okay. So it's... Oh, I know why. It's 9 divided by 1.5. Yeah, 6. Okay. That makes way more sense. Okay. Alright, so I guess I would ask you guys this. Is the decrease uniform? Do we need to do one more just in case? What would the next one be? The next one would be 4.5, right? This line would be 4.5, right? Okay. So what I would ask you guys is this a uniform decrease from 18 to 9 to 6 to 4.5? Is it the same amount of decrease each time? It's not, right? Okay, so this meets the definition of what we set up here. It's a non-constant electric field, and the electric potential is also not uniform. It decreases rapidly and then it slows down, yeah. In fact, if I wanted to properly draw equipotentials here, what I'd probably need to do is to pick a fixed amount by which the potential changes instead of a fixed amount by which the distance changes. Like maybe I want to draw one line for 18 and then the next line for 9, or maybe instead I basically just make it every 9 volts or something. So I do 18 and then 9. The next one would be 0, so that doesn't work very well. But I guess what I was trying to say is, like, these lines are equipotentials, but they don't really give you a picture of the electric field. Ideally, what you'd want to have is the lines here would be closer together, so I need to kind of put one in between. Like, if I wanted to put one for every 1 volt, for example, the lines would get really close in this region here, but then the 1 volt region would separate out like this. Yeah, there's the picture from the book that he just put into the chat, and that picture's perfect. I don't know if it's from the book, but it's from something. And it's a little more accurate because... Nope. The lines on the inside need to be closer together. But I just chose fixed distances here, just so you could see that when you're near the charge, the electric potential is high, and then it gets smaller and smaller and smaller. At an infinite distance, the potential will be 0. Yeah. All right. Do you guys have any questions? All right. So this is a pretty powerful thing we have now. The electric potential due to a point charge. That's really powerful because what we can use it to do is to solve some, what I would say is some pretty difficult problems. This one here. So quite a few of your homework problems are like this problem. So I want to make sure we do this one before we adjourn today. So, moving through a potential difference. I wonder if this is what we just derived. One thing I'll mention is that electric potential is a scalar. So if I have multiple charges, okay, then to find the electric potential total due to multiple charges, you basically can just add up the individual charges. So if I have 2 objects, I can basically just sum the potentials. So if I have one charge here, and another charge here, I can like literally just sum the potentials. Does that make sense? Because it's a scalar. Just like if I have 10 kilograms in a bucket and I add 20 kilograms to the bucket, 10 plus 20 is 30, right? Because mass is a scalar. If I know the electric potential due to one charge, and I know the electric potential due to another charge, right? Then the total potential at some other point is going to be the sum, right? And this problem allows us to kind of use that. So in this problem, we're going to go through this step by step. I'm going to have you guys do some intermediary steps as we're going. A dust particle with a mass of that, 5 micrograms, and a charge Q naught equal to 2.0 nanocoulombs. This is the particle. This is your Q naught right here. It starts from rest and it moves in a straight line from point A to point B. So from here, A to B. We want to find what is its speed at point B. Remember, it starts from rest, right? And we're going to use that equation that I just wrote down combined with our energy equation and then the relationship that Q delta V is equal to change in potential energy to solve this problem. So the first thing I want you guys to do is to calculate this. What is the potential at point A going to be equal to? What is the potential at point A going to be equal to? Can you guys try to calculate that? Keeping in mind that you're going to sum the potential due to the positive charge plus the potential due to the negative charge to find the potential at this point here. What would it be? What is the potential at point A going to be? Okay, one charge is positive 3, one charge is negative 3. At point A, I want to write down the potential. What distance should I use? Do I use 1, 2 centimeters, 3 centimeters? What do I use for the positively charged particle? 0.01, right? It's the distance between the particle to the point, which in this case is 1 centimeter. So this would be 0.01. And then what about this one? We're looking at point A. 0.02, right? Because it's the distance between there and there now, which is 0.02. Yeah, exactly. Now, K is... Can you guys get an answer? Yeah, of course you have to do that. But I mean, keep in mind that if I have 10 to the 9 show up in K, and I put a nano in here, the nano is 10 to the negative 9, right? So the 10 to the negative 9 basically just, again, it kind of annihilates the 10 to the 9. So really you just have 9 times 3 over 0.02 plus 9 times negative 3, 9 times 3 over 0.01 plus 9 times negative 3 over 0.02. That's what you got. What do you get out of this if you calculate this here? What is this step being? So it's ended up being something like K times 3 times 1 over 0.01 minus 1 over 0.02. And this is just like 1 minus a half effectively with 100 up here. 1 minus a half is a half. So 3 over 2. 3 times 9 is 27. 27 divided by 2 is 13.5. Yeah, I agree with you guys. So it's 1350. 1350. And is it positive or negative? Or it's positive, right? This term is bigger than this term. Yeah, joules per Coulomb or just volts. All right, what about point B? What's the voltage at point B going to be? We're going to have... Well, why don't you guys do it yourself now? At point B, you're 0.02 meters away, and then over here it's 0.01. Same but negative, right? Yeah, has to be, right? Has to be. I mean, all you're doing here is you're just changing which one's the denominator, so yeah, it's going to work out that you get negative 1350. Okay. Which point's the higher potential? Point A. That's good because our particle needs to naturally move from point A to point B. If it didn't, then the problem would be kind of silly. And in reality, the particle would actually move to the left. But that's not what happens. So now we know what delta V is, right? So delta V is equal to final minus initial, right? So it's VB minus VA. And that's going to be double this, right? VB is the one that's more negative, and it's in front. So it's going to be negative 1350 minus 1350. So it's going to be 2700, right? With the negative sign in front of it. Okay. Do you guys want to go through the rest of it? The next step is to use work done by non-conservative forces is equal to change in kinetic energy plus change in potential energy. Acknowledge that there's no non-conservative forces acting here. And knowing that the initial kinetic energy is 0, can you guys find out what the velocity at point B is? So this is where it becomes really important to, like, distinguish between your V's. So that's why I've been putting these V's like this, and then when I draw a velocity, we'll try to make it a... Never looks very good. Just... We'll leave the things on top of here for this, and then for when we do velocity, we'll just do... Alright. We'll just do a lowercase v. Which, it's hard to distinguish, right? So, some kind of, like, curly v or something like that. What would the velocity at point B be? Can you guys calculate that? Give you a couple minutes. Just wait to put it in, Ty. Just wait a second. Give people a chance to, like, answer it themselves. Okay. You want to get an answer? You go ahead and put it in the chat if so. 1 times 10 to the 6th. Alright, 2 you got the same answer. Probably right. Let's just go ahead and go through the solution though. So let's define, as it does in the problem, that Q naught is equal to 2 nanocoulombs, and the mass is equal to 5 times 10 to the negative 6 kilograms. And then we'll use those to solve this problem. We also know that it starts off at 0. So what we have is basically the same solution as we did in the last problem. You end up getting negative 2Q times delta V divided by the mass of the particle, and then you take the square root, and that ends up being equal to VB. So in this case, that's the square root of -2 times Q naught, which is 2 nanocoulombs, so 2 times 10 to the -9 coulombs. Delta V is what we calculated, -2700. By the way, you will almost always have these negative signs show up inside of here, right? And it might kind of look bad to you, because it's like, wow, there's a negative sign inside of a square root. That certainly doesn't work, right? But the fact is that if it's a positively charged particle Q, and delta V is negative, you get a positive sign. If it's a negatively charged particle, and delta V is positive, well, again, you're going to get a positive sign, right? You leave the sign of the charge and the sign of delta V in there, and this quantity, even though it's weird that it's got this negative sign, you're still always going to get a positive number out of it. Because either delta V will be negative, or the charge will be positive and delta V will be positive. Did you that is that just a bunch of me rambling, or did that resonate with any of you guys? Shouldn't do that in the middle of a problem, just start talking about random things, but if that negative sign bothers you, don't worry about it, because delta V is either delta V will be negative or Q will be negative. Not both. If they're both negative, then you've got a problem. Alright, so... Yep. 46.4. What does this work out to? Alright, -9 divided by -6 becomes -3. -3, and then this becomes 2.7. So we're left with 4 divided by 5, which is like 0.8 times... Like, there's not an easy way to do this. You gotta put it in a calculator, I guess. You could just like say this is 5. 27 over 5 is about 5. 5 times 10 is... 5 times 2 is 10. Times 2 is 20. Square root of 20 would be... What's the square root of 20? It's a little bit less than 5. I could see how you get 46.4. Did I put the wrong mass in? Oh, I see. That's funny. Because it said 5 times 10 to the -9. But then there's a micro. That's not right, is it? That's a typo in the book. Because micro would be 10 to the -6. This should be nano. Okay, well then I did use the wrong one, because I was scrolled down a little bit. Let's fix it. So this is wrong. This should have been apparently 10 to the -9. And the same thing down here. I'm glad that you guys noticed that. Well, in that case, the answer is going to be a lot bigger by a factor of like square root of 20,000. So, all right, what'd you guys get? What is your answer? Thanks for catching that. Those of you guys that figured out the maps thing. Let's see what we get. Yeah, 46.5. That's what I got. Ooh, turn those things sideways. There we go. 46.5 meters per second. This is actually how we accelerate tiny particles, is by subjecting them to a potential difference, like a gap, and using that to give them kicks of energy. So to tie this back to one of the problems that we did earlier, if you have a scenario where you have a positively charged plate like here, and you put a gap in, so we've got a positively charged plate, and near that we put another negatively charged plate, and let's say that you take a particle, like let's say a proton, so I've got a proton, let's say, and I shoot it into here so that it enters this region with some initial velocity v naught, and I tell you that there's some plate separation here, so there's some delta v, and the delta v might be something like, let's say 100 volts. Let's just use something simple. Then upon going through from point A to point B, this positively charged particle is going to kick out on the other side with a higher speed, right? And we even know now what that value is. The value of this just ends up being 2q, whatever the charge is, times delta v divided by the mass. right? So the bigger that you make delta V, the more of a kick of energy that this charge is going to get, right? This is how we accelerate charged particles to bigger and bigger values, is that we force them to jump through these voltages, right? Are you confused by what I wrote right here, Tyler? Okay, well, wait. Why would the particles... Wait, hold up. You're asking a question, Ash. Why wouldn't the particle just stay still because the charge on either side is equal? You're talking about in the problem that we did? Positive and negative, yeah. I guess you assumed that they were both positive. That's what you're thinking. Yeah, if one's positive and one is negative, then it sets up a potential difference so that it would naturally go from A to B. Yep, it's accelerating to the right, yeah. So Tyler answered your question exactly right. But anyway, so this is how we accelerate charged particles. This is how we get them to higher and higher and higher velocities. We just force them to pass through a region of space where you have some potential difference, and they gain energy as they pass through here, right? They gain some kinetic energy. The amount of kinetic energy they gain, well, that's given by that thing right there, whatever their charge is times delta V. And if you can force the particle to go through these gaps like this multiple times, you can give them more and more and more and more energy. The distance between the plates, does it matter? No. No. It doesn't matter. It would change, I mean... So if you make the plates closer together, the potential difference would stay the same. What would change? Maybe you guys can tell me that. Suppose I take these plates and I move them closer together. What changes? The potential difference won't change. The rate of acceleration would change, exactly. What does that mean about the electric field? Does the electric field get bigger or smaller if we put the plates together? It's not that odd if you think about it. Yeah, the field gets bigger because remember that the electric field is basically equal to negative delta V divided by delta X. So if delta X goes down, but delta V remains constant, the electric field has to get bigger. So yeah, the rate at which they accelerate would be the thing that would change. But the velocity would be the same, yeah, exactly. Assuming that, moving the plates closer together doesn't affect the voltage, which I don't think it would. I have to think about that for a second. I don't think it would. Anyway, so we'll talk later on about how you do this and how you do it in a repetitive way. One option would be to stack together a bunch of systems like this, right? You just take what you have here and just duplicate it over and over again, and you make the particle go in a straight line. But there's a creative way that you can do something that we'll see later on, wherein if you add a magnetic field to the picture, we're going to learn that magnetic fields have this strange effect on particles that they cause them to kind of go in circles. So what you can do is you can basically force this particle to travel back through the same path over and over and over and over again, every time going through the same path, getting that kick of energy. And so once you do something like that, you can basically increase the velocity of the particle as high as you want to in a very small location. Yeah, it's basically how a particle collider works. Yep, exactly. At least the initial part of it, where you're speeding the particles up. You got to get, the place I worked at, we were colliding protons and antiprotons together at velocities that were like extremely close to the speed of light, and this was just the initial system to get it sped up. But then there's multiple other ways that you can increase the speeds. But almost always what you're doing is just you're passing a particle through some voltage, you're giving it a kick of energy. Yeah. Yep. So what I'm describing is more like a cyclotron. A particle collider would be what you'd use the cyclotron. You'd use the cyclotron to speed the particles up, and then once the particles are at that velocity, then you'd force them to collide at a certain point. That'd be the collider part of it. But yeah, that's part of it at least. So okay, so I believe this is a good stopping point. We did not even... We covered most of what I wanted to today, actually.